That's teasing you. Friday. That's super exciting. All right. Thank you, Greg, for the announcement. Welcome, everybody, to our latest installment of AMS Colloquium. I'm your host, Paul Constantine. I'm an assistant professor in the Applied Math and Stats Department. We're very fortunate today to have Professor Fred Hickernell joining us to talk to us about thinking like an applied mathematician and statistician. But before we get started, we will begin with our world-famous colloquium correspondents, Jessica and Izzy, who are going to tell us about trash. Jessica and Izzy. Oh, and you need this thing.
Yes.
There you go.
Hi, everybody. I'm Izzy.
Hi.
Jessica. So, walking around today, Jessica and I were walking campus. We see some trash on the ground, and we're like, where does that go if I don't pick it up? Similarly, you're at the beach maybe over spring break, and some trash washes ashore. Where did that come from? Where is that going to go? Well,
turns out when you Google the appropriate phrase, you find out.
Some researchers at the University of Miami Rosenthal School of Marine and Atmospheric Science, I had to read that one, they were wondering the same thing, and so they made a mathematical model.
So this model it's able to model how trash moves throughout the ocean. So if I throw my water bottle down outside and it eventually makes its way to the ocean, how will it move around? Will it find other friends, or will it be lonely for all of its time? It turns out that it has 5 different chances to find friends, as there are 5 big humps of trash in the ocean, which we can see in this graph.
So the researchers used ocean currents and wind models into their model, and then they corroborated this model with data from NOAA, and they have these buoys that have tracking devices in them, and some of them become unhinged from the ground, and where do they float? And their pattern matched this mathematical model.
Yeah, so kind of the upshoot of this is not only can we model where trash ends up, but we now know how things move throughout the ocean. So we can model shipwrecks, we could model mysterious airplanes that disappear, assuming that they crash. I don't know, we don't need to get into conspiracy theories.
Also ice and everything else. So also something that we kind of like about this is if you're planning a cruise, if you don't want the cruise to go past one of these islands of trash, then it doesn't have to. But if you're doing like a propaganda cruise, then you could happen to go right past one of the big ones. So we thought that was super interesting.
Maybe we should share this with cruise companies.
Yeah. So we wanted to make that one short because our faculty spotlight for today is super, super, super exciting. So we need to intro this. So a lot of the undergrads and anyone who's had the extreme pleasure of being in one of Dr. Navidi's classes knows that he has very distinct mannerisms and a very unique style of teaching. So we're going to model some of those today for those of you who haven't had the pleasure of being in his class.
So we're going to begin by asking, we have this really exciting presentation today, so does anyone, before we start, anyone have any questions?
Any comments?
Maybe a particularly poignant comment out there today? No? Okay, well.
Today we have a multimedia presentation, everybody. Multimedia presentation. And yeah, so anyway, we're really excited about this. We're not making fun of him, but it truly is one of our favorite parts of being in
the
class.
highlight of my Monday, Tuesday, Friday, Wednesday.
So the reason that we're so excited, one of the many reasons we're so excited to spotlight Dr. Navidi is because in all of our interviews with the other faculty we've spotlighted, so many of them have had connections to Dr. Navidi. So in every community, there's a sort of a like a ringleader, or a head honcho, or a godfather, and so we figured out that this person in the math department is none other but our very own Dr. Navidi. Truly, how many people here are here because of Dr. Navidi?
Or maybe he was one of the first friends you made at Mines, or the first people you talked to.
Yeah, everybody is connected. So so many people cited him as their path to minds, so we wanted to know what his path to minds was.
So it turns out that Dr. Navidi has not been here forever. He did, in fact, have another position before he came to Minds. He was at the USC Medical School as a biostatistician. But the thing about this position was that it was, as Dr. Navidi calls, soft money. So all of the money had to come from grants. So he either had to be on his own grant or be on someone else's grant. How many of you would that be slightly stressful for, to know that all of your income comes from grants? Yeah, me too. So I think it's illogical that he would want to transition into a more stable position, which is what Minds had to offer. At the time that he came to Minds, which was 1995, Minds didn't actually have any research statisticians. So he was the first research statistician at Minds, and since being here, we now have between 3 and 4 oscillating research statisticians.
So that's really exciting. And so we asked Dr. Navidi what some of his favorite research projects have been. He said that back when the math department was still part of the Math CS department, he worked on really interesting mobile ad hoc networks with Tracy Camp, and that was something super interesting. It was relatively groundbreaking at the time because it was 10 years ago, and so he really enjoyed doing that. We also
So we asked Dr. Navidi if you could tell everyone in the world and make them understand one concept from statistics, what would you choose?
And this is good timing because April happens to be Math and Statistics Awareness Month. So take that with you for the rest of your April because it's really important. And so, if you or a loved one has been diagnosed with finding statistical significance in too many places, you may be entitled to statistical advice. Dial 1-800-99-NAVIDI now. That's our little PSA. So, following this, we would ask any questions or comments about that, but instead we wanted to know what his ideal answer to when he asks. Any questions, any comments?
And he told us that it would be a comment or a question that reflected that the student was so enthralled with the material that they hadn't stopped thinking about it since last class, and they could not wait to get back into the classroom and ask this question about the material.
So those of you who haven't had him yet or are going to have him next semester, keep that in mind and ask him the best question he's ever been asked. It'll delight him. So Dr. Navidi is just one of those people in our department who is so universally well-liked and well-respected. I don't know a single person who doesn't look up to him as someone that they kind of want to be like when they grow up. So we asked him to give us some advice so we can be more like him when we grow up, and honestly, it's some of the best advice I've ever been given, and so we're going to give it to you and think about it over your weekend, over your week, over your life. So self-confidence is good. It's really good. It's easier to treat other people well if there's no way that they can make you feel bad. And with that,
Math's all folks.
Jessica and Izzy, thank you very much. We're also pleased to be joined by Jessica's dad and brother here today. Also, and Jessica's brother's going to be starting at Minds next year. Well, welcome to the family. Is that what we say? It's now my pleasure to introduce Professor Fred Hickernell. Fred, please join me up here. I'll ask you a couple of questions so we can get to know you a little bit better. Also, our department has a gift for you. Oh, yeah. Yeah. Thank you. Yeah, there's something in the bag too. It's not just a bag. Imagine if we just gave that.
That's all right.
We'd save so much money. Yeah.
So, if I'm American, I open it right now. If I'm Chinese, I open it later.
Let's be Chinese.
Which would you? Let's be Chinese. Good.
You'll notice that the setting for our interview here is the skyline of Hong Kong.
Yes.
Which is the place where you spent some time.
Yes.
Thank you for visiting us here at School of Minds for AMS Colloquium. You're professor and chair of the Applied Math Department at Illinois Institute of Technology, which is where Greg came from recently. You've been there since 2005. Before that, you were at Hong Kong Baptist University for about 20 years. Yep. So according to your CV, you've written about 119 academic articles. Which one is your favorite and why? Why?
I was primed for this question, and I felt it's like, which one of my children is my favorite? Although I have fewer children than articles. So let me speak a bit about an article. The title is something like a generalized discrepancy. It's the one that's the most cited, and one where the early articles where I used reproducing kernel Hilbert spaces. Greg knows a lot about reproducing kernel Hilbert spaces to show how to derive error bounds for multiple integral quadrature or cubature problems. And since it was one of the first ones, people then built on that, and it seemed to spawn a lot of interest in that direction that helped us to know how good different cubature methods were.
Yeah, via discrepancies.
Via discrepancy. So its discrepancy was a long time before, but I was able to make it a little more general.
Okay, put a spin on it. So you're well known for your work in numerical methods for integration. Where do you find interesting integrals in real world applications?
Okay. So one area that spawned a lot of research in the Monte Carlo and quasi-Monte Carlo, these multiple integral problems, was finance problems, pricing options. They can be integrals of dimension 2 up through hundreds. Another area, one of my recent students who just graduated was working with physicists at Fermilab. It's a Department of Energy lab where they smash particles near Chicago, and they use integrals to try to understand what they detect is telling them what's happening, because they can't. They have to do some inference, but there's high dimensional integrals that come up there. Sobel indices is another area. Inference, just you need to compute a probability, and sometimes it's a probability of a multidimensional probability. That's a few.
So, integrals everywhere. Lots of places.
That's nice of you to say, right. Lots of places.
So your work spans applied math and statistics, sort of
Right.
lives at this border also.
Right.
What are some interesting problems at that interface?
Okay. So I'm going to talk a bit today about the problem of evaluating integral and how statistical perspectives and applied math perspectives come together in that. Other work on if you have some data and you want to approximate a function, it's a similar problem, but you can either take the applied math reproducing kernel Hilbert space approach, you can take the Krieging approach, and they're like parallel approaches but from two communities. And then a third area is experimental design, which I've done a little work on. So I didn't bring my water bottle, but look at Paul's water bottle from MCQMC, and it has all these little squares with points on them, and they're points that are used for integration, but sometimes in design of computer experiments or design of even laboratory experiments, you want to place points well in a region. And so the statisticians have done a lot of work. Sometimes they use methods from algebra, and the applied mathematicians also are interested in that problem.
Dots and boxes.
Dots and boxes,
Yeah.
correct.
So what sort of things do you do outside of applied and computational math?
I enjoy spending time with my children.
Okay, all 119 of them?
No, 2 of them
Okay.
who are in college but close by.
Okay.
And I enjoy good food. And we were talking about Chinese food. That's another thing. Yeah, those are a couple of things.
Great. Well, we're looking forward to your talk. Let me cue it up here and then get you going. And you're all set. And Professor Hickernell.
Thank you. So let me ask you, how many of you would consider yourselves applied mathematicians? Could you raise your hands? How many would consider yourselves statisticians? Raise your hands. How many would consider yourselves both? Raise your hands. A few. Okay, good. Neither? A few. Okay, okay. So the main purpose of my talk is to encourage you who are applied mathematicians to also think like a statistician. Those of you who are statisticians to also think like an applied mathematician. And we're going to look at a problem that's a fairly simple problem to pose. I'll be going through lots of different things, but rather in summary or highlighting. And I have some slides at the end to share that for people who want to stay for the discussion. So I'm going to tell a story about Amy, who's an applied mathematician. And Amy is doing some financial modeling. And as I mentioned, you can use, you can model option prices as integrals. So she had this integral. The payoff is some function that, in this case, an arithmetic mean call option. This is the strike price. You don't need to know the details, but it's a function that can be coded. It's a function you can write down, but it's not necessarily a simple function to integrate. This probability density function here comes from the PDF for a Brownian motion at d different times. So again, all the parameters in here are known, but you can't really do the integral except for d equals 1, and then you could write it down in terms of special functions. And Amy's wandered down to the faculty lounge, and she runs into Sue, who's a statistician. And Sue has an integral that she would like to evaluate, and it's a probability. So again, we have this look the same. That's coincidental. Your application doesn't have to be that way. If this was over the whole real line, then please someone tell me what's the value of the integral. Yes, did you have it? Okay, 1. So, but if it's a box, and if sigma is not diagonal, if sigma is diagonal, then things are easy. But sigma may not be diagonal, then this is not easy to do even in dimension 2. So Amy runs into Sue, and they say, OK, you've got an integral, I've got an integral, let's see what we can do. So the first thing, Amy remembers her Calculus 1, where she did integrals over 1 dimension. Let's say the midpoint rule, but choose your favorite. And the midpoint rule has error of order m to the minus 2, where m is the number of points that you have. And so if you look in this box, we have 8 points in one direction. And so Amy says, well, we can do this in higher dimensions. We're going to integrate just over the simple unit cube. And here's what it looks like. And the error is still order m to the minus 2, provided that the function has enough partial derivatives up to order 2 in each direction. But then as she's thinking a little more, she realizes that how many points is this? OK, if we count this, we see 64. That's the number of points if the dimension is 2. If the dimension is 3, this is not 64 points, it's 512 points. And so as we're thinking about this, and this is the same except now x1, x3, she does a few computations, and if the dimension gets up to, let's say, 10, it's going to be 1 billion points. And the error might be good, but the error doesn't really look like the number of points to the minus 2. It looks like the number of points to the exponent 2 over d. So when d gets large, this is going to be a small number, and the error is not going to go to 0 very quickly. OK, so this is a bad idea, and I'm not going to show you any examples with. It's a bad idea when d gets, let's say, more than 2 or 3. So being a bit discouraged, Sue reads the Wall Street Journal. And in the Wall Street Journal, in August of last year, there was this interesting article on Monte Carlo. And one of the experts in Monte Carlo, Art Owen, who visited you last year, talks about Monte Carlo as where you take generate random scenarios, and then you see what happens, and this can give you the answer. So Sue is thinking about their integrals, and Sue decides, this integral, which was some function integrated with respect to x, if I split it into a part that's the integrand, I split it into parts that's the PDF, then I can think of this as the expected value of some function of x, where x is distributed according to this PDF row. And then this is the sample mean. So I'll just take samples randomly, IID. And then what I'll do is I'll use the central limit theorem, because this sample mean will be approximately normally distributed. So I can say that my error will be proportional roughly to 1 over root n. It's not very fast, but it's better than grids. And I can get the answer right about 99% of the time, as long as I know what the standard deviation is. And so what Sue did here was to take the sample standard deviation and multiply it by an inflation factor, just so we don't underestimate the variance. So this is a first attempt, and we avoid this problem of high dimensions causing us trouble. And it's a reasonable attempt, but we have a little problem, and that is the central limit theorem only is true as n goes to infinity. It's not true for, let's say, n equals 100 necessarily. It's true for large n, but how big should n be? That's a big question. Also, it depends on knowing the true standard deviation, which we don't know this true standard deviation, we're just estimating, and this could be overly optimistic. So one way, and I won't tell you the details now, but you can ask me later, is we can replace this interlimit theorem by a Bayesian inequality, which is a finite version. We can also use Cantel's inequality to be sure that this is a good upper bound. And what we can do then, it has a rigorous error estimate and say that if we want the answer right at least 99% of the time, we can do something that looks like this, but it's a little more complicated. And that's recent work with a PhD student. So let's look at Sue's problem. I'm going to pick a particular A and B, not too large of a dimension, but just so that I can, that's not so important. The answer should be less than 1, right, because it's a probability. So if I wrote 1.6, then you would be a little worried. But 0.6, you can maybe believe me that this is the right answer. And so when we use this idea, and what I'm not talking about so explicitly, but basically, here's a relative error tolerance, and our method stops when it has reached the error, not because it knows the answer, but because it thinks it knows the answer. And it works out all the times we tried it, meaning 100 trials. But it takes about 1 million samples. So this is kind of a lot. But it took about 0.1, 0.2 seconds. Now, one thing that Amy does is she looks at this, and the transformation we had before was just to take this AB and shift it and stretch it and an affine transformation and get it onto the unit cube. But Amy, talking to her uncle Alan Gens at Washington State, comes up with a better transformation, still using IID sampling, and now we can drop it from about 1 million points to 80,000 points, and the time drops by about a factor of 10. So just making a variable transformation can sometimes help us out. Okay, but we go on. If we make the tolerance smaller, we're back up to a couple million. And a couple million's not that slow, but if you want to do this a lot of times, we might see what can we do better. So the problem is that we have this root in. This is a slide I showed you before. And so you want to find something that the error can be better than root in, 1 over root in. So Amy suggests not IID sampling, but sampling in a way that is more even. So these points are not IID. IID, point number 2, knows nothing about point number 1. So it may be close, it may be far, but they don't know anything about each other. Sobel sampling, which relies on finite fields and number theory, makes points that are more evenly spread. And let me show you in what sense. If I take, these are long strips, 1 over 64 in area, or tiles if you wish. Each of them contains 1 point exactly. If I make them now 1/32 by 1/2, they still each contain 1 point, and so forth. 1/4 by 1/16, 1/8 by 1/8. And that's x1 and x2. When I change to x3 and x5, I'm not quite as good. I need to make the tiles or the strips twice as big, but each of them contains 2 points. If the dimension is large, I may not be able to make them just to contain 1 point, but they will contain, let's say, a certain power of 2, and as you increase the number of points, you can make the strips smaller and smaller. Okay, so Amy needs to figure out how the error is going to be, and so I'm going to briefly mention the way to do it. We assume that the function is in a Hilbert space. A Hilbert space is a vector space with an inner product. And because it is, and because this mean or this integral is a bounded linear functional, and so is our approximation, and so is the error, we can write the error exactly as the inner product between two functions. This is a function, the error representer, and this is the integrand. And then we can use the Cauchy-Schwartz inequality, or actually just write it out as the size or the norm of the integrand, the size of this error representative, which is actually right here explicitly. So this needs to be a special kind of Hilbert space, one for which we know it's reproducing kernel, and then times the cosine. So the cosine is between plus and minus 1. And so what this tells us is if we can make the function smaller, that's good, but we can't always control the function. If we can make this smaller, which means we choose the points well. So for IID, this is into the minus 1/2. For these good Sobel points, it's into the minus 1, and that helps. Okay, so here's Sue's problem, Gaussian probability, with the Sobel points using the same Gens transformation. Now we've dropped to 1,000. Actually, probably could be smaller, but in my software, I start off with 1,000 as the default number of points. And the time has dropped now to milliseconds instead of tenths of a second. 10 to the minus 3, it should go down by a factor of 10, but because this 1,000 was the default minimum, it's now up to 2,000. And if we go, we'll go further a little later. Now, Sue sees this, and she likes the points, but she says, you know, you have bias, meaning that the expected value of your answer is not the answer. Well, of course we have bias because nothing's random. When we went to these Sobel points, we're not random. But Sue is clever, and she says, you know, we can scramble these, still keeping this beautiful structure that these strips have the same number of points, but now under this random scrambling, the expected value is the same as the true value. And the error can be even smaller by a power into the 1/2 if the integrand is smooth enough. Okay, so Amy gave us scrambled points, Sue gave us Sobel points. Sobel gave us Sobel points. Yeah. Amy discovered Sobel points, suggested Sobel points. Sue suggested Art Owen's random scrambling. And so now, this is just showing you that we have the same good structure. And then there's another kind of points that we'll see a little later on. Those are lattice points, and they can be randomly shifted. You don't get the extra power of 1/2, but you do lose the bias. Okay, so what do we have now? We started off with original IID with a bad transformation. We had 1,000,000 points. Sobel dropped us to 1,000 points. Scrambled Sobel, we would hope, would get us even better. It's not. So some of the things I'm telling you are things I've known and people have known for a long time. I do not know, well, this is the minimum, but I still don't know why, for example, down here, it's not better. Because the real error is much smaller, even smaller than we need to be. Because the real error only needs to be 0.67 times 10 to the minus 3. So it should be about 6 or 7 times 10 to the minus 4. This is conservative, because these errors are smaller. We can accept that. So this is giving us a smaller actual error, but it's not telling us to stop sooner. I don't know the answer. But there are some things in this talk I just don't know the answer yet. But if I knew all the answer, it would be old and stale, and we can talk about it. Okay, so now I'm going to stick with the scrambling because we like Sue's better no bias answers. Drop the error tolerance again, and we're down here again. It's sort of only a couple of hundredths of a second to get our answer, about 10,000 points, not too bad. Okay, so I would like to talk about Amy's problem. Okay, remember, Amy wanted to do option pricing, so we've talked about Sue, and Amy's been chomping at the bit. Try my problem, please. Okay, so this is a little higher dimension. This is dimension 12. Maybe didn't say it here. This is dimension 12. It's an Asian call option, so you take the mean of the stock price. This is the model of the stock price. You may not be able to absorb it, but the key thing is that to get the points x here, we need to multiply them by a matrix A. And that matrix A times its transpose has to be this matrix, which is basically the covariance of the Brownian motion at different points. Now, this is not unique. AA transpose, there are many solutions because I can multiply A on the right by a orthonormal matrix, and then a transpose have that transpose, and they would cancel out. Okay. But this is the Cholesky decomposition, so this is one way. And this is also the way that's used if we say the first element of this vector z tells us to march forward the first time step, and then the second element tells us from the first time step to the second how far to go. So this is one choice that is used. And for IID, actually doesn't make a difference. But for Sobel, it will. Here we have not 100% accuracy. This means that this integrand is not falling within that, quite within the set of integrands for which our theorem holds. And that's a little sad, but I can't quite explain it, but I have some better news, because after Amy was looking at this much faster, okay, well, somewhat faster, smaller n, Amy said, you know, you should use principal component analysis, which is basically choosing the A in terms of the eigenvectors. And the reason this is going to help is because stock options, a lot of them depend on the gross or large scale, not the fine scale behavior of the stock. And that's what is captured if we use an A that is based on principal component analysis. And now we get back to 100%, which is nice. And we have a smaller n, and we have a smaller time. Okay, so twice actually in this talk, I've talked about a different way of writing the integrand, and you can get a better answer. I've also talked about so far that if we use these more even sampling, and I should say, sorry, these are both scrambled Sobel, we can get a better answer. So we've tried a couple things, and we've improved over grids and over IID. Okay, then Sue has another idea. Says, look, in Monte Carlo we use control variates. Why don't you try control variates? Because in this particular problem, there's a related option, the geometric mean, which we can price exactly. And if you know the answer to a similar integral exactly, you can use that to increase your accuracy. Now, I said increase the accuracy. We're stopping, we have this automatic stopping, and we're missing some of the time, a few percent of the time. But we're cutting the time in half because we're cutting the sample size, in fact, by about a factor 4. Okay. And the control variates for low discrepancy sampling is different than IID, and a recent paper, it tells us how to do that. Okay. Now here's a third way. So we've talked about IID Monte Carlo, we've talked about low discrepancy, we've talked about now Bayesian cubature. So Sue has another idea, and Sue says, I'm not going to assume my function is in some Hilbert space. I'm not going to assume my function is just L2, which we need for IID Monte Carlo. I'm going to assume my function is random, a stochastic process. In fact, a stochastic process where if you evaluate the function at any particular point in x, it's a normal random variable. Now, this is a little different assumption of randomness, and when Sue is assuming that it is random, that's a big assumption, because I can generate random numbers from my random number generator, and if it's a good random number generator, I'm confident that those random numbers look like the random numbers that they're supposed to look like. But since this integrand gets handed to me by the person who has the application, there is nothing usually in the integrand that's saying, I come from a Gaussian process with, okay, mean is 0 for convenience right now, but why this covariance kernel? Why? I don't know why, but I'm going to try it, and we're going to see if it works. Okay? That's what we do. That's what Sue wants. I mean, Sue and Amy are very entrepreneurial, and I like their spirit, which is why I'm telling you about them. So what we do, this C is a function, and we find out that the best weights are not necessarily 1 over n or equal weights, but they satisfy a system of linear equations. The weights times, or this matrix C times the weights is this other vector C, which depends on this covariance kernel. Now again, we don't know what it is, but we're going to find it, so hold tight. And then the error we could write as a normal 0, 1, standard normal random variable. So this looks complicated, but it's basically a standard normal random variable times something that only depends on the covariance C and the points where you decide to sample the integrand, and something that says how big is the integrand. These y's are the function values at the x's. Now, if this is true, and it is true under the assumptions we've made, then we can use, this is strictly normal, not just approximately normal, then we can say that the probability that the error is less than or equal to this quantity here with this 2.58. Okay, why is it 2.58? Those of you who are statisticians?
Gaussian 99%.
Gaussian 99%, thank you. So if you don't want 99%, if you want 95%, this becomes 1.96. Oh, you're great. Okay, how about 99.9%? 99.9%.
99.9%. I don't know that one.
Okay, I feel better because I don't remember either. But I'm impressed. Very good. Okay, so here we are, and we have a way to know, because I'm showing you these examples, and I'm not telling you the details, but I'm giving relative or absolute errors to my algorithms, and I'm stopping when I think I have the right answer, which is not an easy problem. And the details of how we do that is in the slides for after the talk, or in the papers. Okay, but let's come back to this problem. The S, which is sort of the vertical scale of the function, that's easy to do by maximum likelihood. The theta is a little more complicated, but you can write it down. But here's the problem. You see this C inverse. So C inverse times Y, that's a matrix operation. So typically that should take order n to the power 3. Good, an applied mathematician. You know a little linear algebra, right?
A little bit.
Yeah, a little bit, numerical linear algebra. Okay. So I have a method that's order n. And if it tells me order n cubed to get my method, that's a pretty costly process. So Amy, who's been standing on the sidelines for a few minutes here, says, you know, you should choose a nice kernel. I mean, you get to choose anyways. You get to assume. Why not choose a covariance kernel for which this C will have a nice structure? For these lattice points, it's basically circulant. And therefore, now, why? Well, who knows why? But nobody told us which kernel, covariance kernel anyway, so we get to choose what we want. And we're going to see if it works in just a minute. Okay? So choose the C nicely so that this doesn't cost too much to do this inverse. And all the maximum likelihood also involves determinants and things that will also be order n log n if you have a nice covariance kernel. One thing too, Amy says, you know, all of this looks like what I did for the reproducing kernel, except I called it K and you call it C, and they agree that that's the case. And then there's another story where Amy says, you know, I can do everything you did without assuming any statistics. But that can't come into this talk, but it's in the slides after this talk. Okay, so here we go, Bayesian cubature. For Sue's problem, moderate relative error tolerance, faster, about the same number of points. Why doesn't this change? Because 1,000 or 2 to the 10 is my minimum. Okay, so these don't n and time and error don't quite follow because there is some overhead in the algorithm and because I have some minimums. But even down here, okay, faster than scrambled Sobo and a little faster than scrambled Sobo and fewer points. So it works. In fact, it worked. It's only supposed to work 95% of the time, or 99% of the time, but it worked. And I can't really say 100 because I'm only doing 100 samples. If I'm only doing 100 samples, actually, this is plus or minus 10%. Okay, just because I didn't have the time to do more. But so roughly 100% accuracy. Probably not 110% accuracy. Okay, then we have Amy's problem, the option pricing problem. And we again get a little faster in. When I say worst percent out of the 100 samples, I took the worst in. The top, the one that's the 90%, well, in the top 10 worst percent. So the worst 10% would be this or above. 90% or below this. And the time, a little worse in this case. I'm not sure why. And this is only two examples to show proof of concept, because this work is not as mature, at least in what I've been doing with my students. Okay. So now I'd like to finish off with some remarks. Some of you said you were applied mathematicians, some of you said you were statisticians, and a few said you were both. So my goal, if you feel like Amy is to meet a Sue, or if you feel like Sue is to meet an Amy, or applied math doesn't have to come first, so it could be a Sarah and an Ann, but also not just to be an Amy or a Sue, but really to be an Amy Sue. I tried to pick names that would be good compound names, because I think as we learn to think about applied mathematics and statistics together, I mean, what I've talked about, admittedly very hurriedly, half of it about would not work without applied mathematics or without statistics. And it helps to be able to understand both. So I can't claim that every problem benefits, but I think there are several, and Paul asked me about a few that do. So I would encourage you to try to think like both an applied mathematician and a statistician. The second thing, and this is something that was sort of hidden, Xiaoli Meng, who's a professor at Harvard, gave a talk about a year and a half ago. Actually, he's still giving the talk, so it's a good idea, where he takes error between the true mean and the sample mean. In my case, we have an integral and the approximation, and he writes the error as a trio identity, 3 terms. And a lot of us in this work had worked with 2 terms, or sometimes 1, because we kind of ignore the other one. But I think it's very helpful to think of all 3. They're hidden back there in the slides, if you'd like to take a look. I have written more about this in a recent paper that's under review. And Xiaoli Meng's paper is still being written, although he started before me. He's a very busy guy, and I fully understand. But he's a very smart guy, and I thank him for this contribution. One is sort of the size of the function. The other is how well you choose the sites, or in statistics we would say the design, or the discrepancy, I called it in one case. And then there's this other part that's typically between plus and minus 1. And it didn't have a name before. I've called it the confounding, but we could discuss that. Normally this is the one that's ignored, but I think it's a good one to keep. And the third thing is I've showed you some integrals that automatically tune the parameters, typically the sample size, but we also used MLE to tune the parameters in the assumed covariance of the Gaussian process. And I think it's a challenging problem, but I think it's an interesting problem, because I think it's helpful to have algorithms that for the user, they can say, here is my integrand, please integrate it for me quickly. And they don't have to turn all the knobs. And too often in our theory, we say, here's the error, but we don't tell you when to stop the simulation. And that's what a lot of my recent research has been about. And I hope you can see, at least from the examples, that we are often successful, although we still have a little ways to go. Thank you.
Time for questions? Yep.
So you used a PCA there.
Excuse me? I didn't quite catch you.
PCA?
Yes.
2 questions about that.
Yes.
First of all, were you just using it were you actually dropping the dimension?
No.
So you just use it to normalize everything?
Right. So the reason is that the Sobel points, if you look at the projections in the first few coordinates, they're really even. If you look at the higher dimensions, not quite so good. So if you can put more of the interesting stuff in the low dimensions, then you're going to get better performance. Asymptotically, it's always into the minus 1 or into the minus 1.5. The plus epsilon I said is because there's some log-in factors, and they're sometimes proportional to d, but that's it's a longer story than I've said, but the idea was to put the important stuff, shove it into the lower coordinates, and then Sobel or lattices or whatever will do better. And that was the idea. But I didn't drop anything, right?
I've got one. So you have a perspective that is your Bayesian cubature, where you have to set this covariance kernel. I won't say choose because that's kind of a loaded word, but you have to set the covariance.
Whatever, yeah.
And then in the reproducing kernel Hubbard space perspective,
yes,
you have to choose also, you have to set a kernel.
No.
So,
yes.
Okay.
Yes or no?
Yes or no? Are these the same question, just from different perspectives?
Yes or no? Okay, let me tell you. That's a good question.
Thank you.
But there's a yes answer and there's a no answer, like a question. Okay, let me, excuse me. Okay, here, this all depends on the choice of a kernel. So that's the yes part. This part here, where we develop the adaptive stopping criterion, we do not assume a kernel. What we do is a Fourier analysis of the function. So we actually don't use this explicitly for our adaptive stopping rules. We do a Fourier analysis, and then we use discrete Fourier coefficients to tell us when to stop. And it is kernel free.
Okay.
Not only mesh free, but kernel free. Okay. But every one of my methods only works if the function is nice enough in some sense, and to say what nice means takes more than hand waving, but it's in the paper. Nice in this case, but it has nothing to do with the kernel. Yes, it has to do with how the Fourier coefficients decay. Okay, this part where we have here, we are choosing the kernel, and the error bound depends explicitly on the kernel. So this C matrix depends on this, and this depends on theta. I just didn't write theta everywhere. So yes, it does. It depends on the family of kernels, and you could have larger families and then more complicated maximum likelihood. And as I mentioned, Amy said, well, I can do this all without statistics, and then she would also have to do the same sort of picking her reproducing kernel. So it would be change the name of C to K. Everything else would look the same, and the only tricky part is, what does it mean to do maximum likelihood estimation without statistics?
It's a great question.
Yes, well, the answer is further down in the slides.
I have a question on the slide, which is, so I'm a spatial statistician, so I think of this C theta in the Gaussian process as something that generates data. And chosen one or selected.
Right, exactly.
Does it matter if they're not that similar? How does the one that generates the function versus the one you choose to integrate? How does that?
That's a very good question. So I'm going to pretend that you're Michael Stein, who's a spatial statistician who lives down the road from. Do you, Michael?
Well, I haven't met him, but yes.
Okay. So one thing he would say is, why are your kernels not necessarily isotropic? I mean, because I pick directions, and I would say, because my functions may not be, or because I can do the analysis or the computation easier that way. So there's a lot of, I would say, philosophical questions. So the function that's generating my data, so here's the data, f of xi. The nice thing is I get to choose the xi, which if you're putting measurement stations, maybe you do, but maybe sometimes not so easily. And I don't know what this function is that well. This is supposed to be like a black box algorithm. So what I'm doing is I'm trying to infer what's a reasonable covariance kernel that this function would come from. I mean, it probably comes from many, but I would like it to be in the middle 99% rather than out in the extreme 1%. So you're thinking of it maybe from the kernel generates the data. I'm thinking of it, I have a function that generates data, but I still am going to be dealing with data. I just get to choose my designs maybe much more easily in some sense than you do because I'm doing them by computer. Although if I was doing computer experiments and trying to construct surrogates for computer experiments, it would be the same type of problem.
I guess guess the question is, some of those C's will fit the data better than others, and so suppose you select...
Right, so that's basically the maximum likelihood problem.
Yeah.
That's basically the maximum likelihood problem.
But you're still sort of with this parameter there, you're focusing on a family of...
A family, right. So only within the family that I choose.
I guess Aaron's question is still valid. Are you in the right family? How do you choose your family? Does it have to have...
Right.
What?
But I could say the same thing to him. I mean,
No,
right, you know, like say if you like Matern, are you going to Matern of all smoothnesses or just Matern with a peakiness? I don't know. Or at least I don't know any better than the statisticians, but it does sometimes work.
Oh, I'm not saying it doesn't work. I was just curious if you chose something that was quite different, if how well it was
Okay, I did some experiments where I chose a Matern. This is not the Matern. It still worked pretty well, but we haven't really experimented enough with different families so that I can say, for all my examples are still limited, this works a lot of the time. That's still a question that needs more investigation. But I would something I know a little bit better about, back when we were choosing the reproducing kernel, which is the same thing, and the discrepancy, if they all come from the same family of smoothness, they all have the same rate of decay. Now, rate of decay may not mean a lot because we want sample size fixed, not sample size infinity, but it tells me that different kernels that have similar features tend to give similar answers. Whether my family is big enough, I don't know. Yeah, that's a good question.
Thank you.
Fred, at least for this audience, you could tell them that you could do even better by doing interlacing.
You mean a higher order?
Yeah.
So yes.
So one could do more than negative 1.5. One could do 3.5. So that's easy.
May I say yes and no? I'll say yes and no for the following reason. For the Gaussian probability, it's a very smooth integrand. For option pricing problems, they're not smooth. So actually, for the Gaussian probability, I can get into the minus 1.5 just with the scrambling. For the option pricing, I can't. I just get into the minus 1. So if smoothness allows, okay, but personally, and Joseph Dick may have a different view, I have never been able to get very high by trying the interlacing of the higher order nets to get very high. And you can do periodizing transformations with the shifted lattice and theoretically get very high. But in the higher dimensions, the theoretically very high may only happen in way past where you want to go, in my experience. So I think this is still a question to wrestle with. The other thing is you just choose a family of kernels that's smooth enough for this type of Kriging Bayesian cubature that may also give it to you, as long as it doesn't take you forever to do the maximum likelihood. So I think there's a lot more to do here. Yeah.
I think your no is the right answer because I did show it to Joseph.
Yeah.
That it wasn't working. We had a good discussion on it. I gave a code. This is where it's not working.
Yeah.
This is where it's working. So you are absolutely right on that. So one of the reasons I thought it was working in your case was because the smoothness wasn't clear to me. So this is the key part. So if it's extremely smooth, you can do a lot.
Here is very smooth. Here is not, because this payoff has a max with 0 and you get kinks.
And also, I think theoretically, this number theory tells us we can do better, but practically, it doesn't. It depends on the bits. So
Yeah.
3 is 4.
Yeah.
So there is one wrong thing, one wrong thing.
I'm going to take one last question, if that's all right. So at a high level, you've described a applied math and a statistics perspective for the integration problem.
Yes.
Are there comparable parallels for the approximation problem?
Oh, definitely.
Spanning function? So like
Greg could answer the question
radial basis
better.
functions versus Kriging.
Yeah, well,
Yes.
I talked.
Yeah, I know, but I'm asking.
Didn't you hear us talk? Didn't you hear us talking?
I'm asking our guests.
So, okay, F, here, let me just give the quick answer.
It's good to get more.
Because F is a Gaussian process with some covariance kernel. Or F is in a reproducing kernel Hilbert space with some reproducing kernel.
that everything you do except MLE, which is in my secret slides below, you can do in parallel. And for those who don't want to stay around for the secret slides below, basically MLE can be interpreted purely geometrically. And then someone has said, well, where do you get the 2.58 without statistics? Okay, I give up on that one. 2.58 or 5 or 2, that I cannot explain except with some statistics. But MLE can be interpreted purely geometrically for a reproducing kernel Hilbert space. So all we're doing here is approximating the function and integrating the approximation. Or that's one way to think about it. So reproducing kernels or Kriging, same thing.
Okay, with that, let's thank Fred.